cheap solar power, batteries, and electric vehicles are changing the transport and energy sector as we know. I bring in guests to this podcast who will help you with their ideas to navigate this energy transition. By the way, this episode is also available as a video on our YouTube channel. Just search Energypreneurs. Thank you for joining. Good afternoon from Manila. Where are you today?
Good afternoon. I'm in Brisbane, in Queensland.
Lovely. Weather must be nice. So not like raining here very badly.
It didn't start off too well. Not a lot of solar this morning with some fog around, but it fined up and warmed up. Very pleasant.
Wonderful. Expecting a lot to learn from you where hydropower is. And maybe before we go there, if you could introduce yourself, Mike.
Sure. Mike Westerman. I lead the hydropower team within GHD. GHD is an Australian consultant. Started off in Australia, now spread across the world, but almost 100 years old and a very strong reputation in the water industry, in dams and in geotech work, but also very strong in the US with mainly an environmental team over there. But we're also in Canada where we do hydro work as well.
Yeah, hydropower is sort of the oldest form of renewable energy that we humans started exploiting.
Yeah, it's probably beaten to the punch in that regard by wind power, because I think we started off using wind for all sorts of uses, even further back, but certainly hydropower in terms of energy storage and having energy on demand. Hydropower is not dependent on the weather. As long as you've got water, you can keep running. It's very early use for driving mills to crush grain and also to pump water. It does, as you say, have a very long history. And in terms of generating electricity, it was probably around virtually as soon as electricity started to be exploited commercially, with the power station at Niagara Falls was built about the time when Edison and Tesla were fighting it out as to which form of electricity we were going to use. So yeah, it's been around for a very long time.
So you're saying that Niagara is the oldest hydropower, right?
I wouldn't say it's the oldest. It's certainly the oldest in United States. And the power station I'm referring has been decommissioned. It's the original one that's no longer in service, but there is a very large hydropower station on both the US and the Canada sides of the border, and there's also pumped hydro on both sides of the border as well, and that's so that they can manipulate the flow over the falls so that during the day when all the visitors are there, there's more water flowing than at night when you can't see how much water is going over. And those pumped hydro facilities have likewise been in service for quite a long time now, I think about 70 years. And pumped hydro was probably most popular around about 70 years ago. In Australia, we had Tumut 3, which was the first pumped hydro built in Australia, and that was commissioned in 74. 50 years ago, 60 years ago, and then followed by the Shoalhaven scheme, which was commissioned in the late 70s, early 80s, and then Wivenhoe, the one just up the road from me here, which was commissioned in 85. And I worked on that as a young graduate, fresh out of university. So it was 45 years ago.
Yeah, these pumped hydro, these are the sort of largest batteries or storage that is available or was available, right?
Yeah, about 90% of the world's storage is still in the form of pumped hydros. So it is by far and away the biggest form of storage. And originally, back in the day, it was primarily to provide a reserve for large coal and nuclear power stations. And so Japan built a very large number of pumped hydro schemes, as did the US, primarily as spinning reserve for their nuclear power stations and also for load following of their nuclear power stations. Because in those days, Japan didn't have any gas and the US had relatively meagre supplies of gas prior to the fracking campaign that's delivered much more natural gas to their market.
Yeah. So for some of my listeners who may not know, so pumped hydro is not a different kind of hydro. It's the same hydro. You basically pump water back, increase your storage so that it can use it other times. So it's the same water gets used multiple times.
Exactly. Certainly that's the case for what we call closed loop schemes. There are some schemes that are open loop, that one of the reservoirs may actually be on a river and there may be water flowing in through the system. But essentially for the pumped hydro itself, the same water is used over and over again, and the machines themselves are somewhat similar to conventional hydros. The main difference being that they're designed as pumps in the first instance, and they run backwards. Or in the case of Wivenhoe and Tumut 3 and one of the units or one of the stations at Shoalhaven, there are actually two hydraulic machines on the same shaft. So you have a pump and a turbine on one shaft, and it continues to spin in one direction, but you close off the water to one or other of those machines. That's called a ternary machine. That's probably 1 in 10 machines of that sort. Most of them these days are reversible. So they're a pump that runs backwards as the turbine when you need to generate, and then it can pump.
Yeah, the way I explain sometimes, it's like a ceiling fan using electricity running, but you put inside water. When the water runs, electricity comes out, in the simplest form of analogy.
Yeah, and essentially in both cases, in both directions, it's using water and the very high density of water and the convenience of water, the way it flows, the viscosity. So it's using all those characteristics of water and then combining it with gravity to either push against gravity to increase the potential energy, or to go with gravity and extract potential energy. In both cases, converting it to mechanical energy and then to electrical energy. And very efficiently. People are often surprised that large pump turbines in the pump directions are up around 96% mechanical efficiency. So very efficient machines.
Yeah, on efficiency, the other question I have, I was the project officer for Toktogul Hydropower in Kyrgyz Republic. I think 1,300 megawatt, that the 4 turbine we replaced. But these were, again, 50-year-old. When you replaced, we got more megawatt out of the same head, everything else, because the much efficient way of transforming. You want to explain a bit how hydropower has become efficient over the years?
Back in the day, when I first started 45 years ago, we still used what were called skins, which were essentially profiles which showed what the blade shape should be at a particular location on the blade. And they were profiles that were put there, and the blades were then ground from stainless steel by hand. And they were designed on the basis of hydraulic similarity to small models. And the models were 300 mil diameter typically. And then they were scaled up. And of course, the small models for a start had a certain level of imperfection. And then the scaling up to the very large machines either duplicated or accentuated that imperfection. Whereas these days, we start off with a computational fluid dynamics model, and we can get incredibly accurate depictions of the pressure profiles across the blades and the flow through the blades. So we're starting off from a much better place in terms of understanding what's happening on the blade in a way we could never do with measuring on a physical model. And then in scaling up from that to the full scale, most of that work now is done by computer-driven milling machines and grinding machines. And then it's checked with a laser so that the accuracy between the model and the prototype now is within 0.1 of a millimeter. A combination of being able to analyze more accurately and then replicate more accurately has meant now that we've got very high efficiencies in the actual water passages. And then I guess the other thing that's happened is that our understanding of where the losses are occurring and optimization of bearings and optimization of the thrust on the machine and the velocity recovery in the draft tube, all of those elements coming together have led to those improvements.
So efficiency, how has it changed in the last 50 years, you would say?
In my lifetime, we've probably increased the efficiency by 5 or 6% on the hydraulic machine and probably 0.5% on the electrical machine. Yeah, those sort of order of magnitude. But most of the losses in a pumped hydro are actually occurring in the waterway. And again, our techniques for tunneling and for lining tunnels, for boring tunnels, have become much more sophisticated. And so we've been able to model those and optimize those and improve some of the round trip efficiencies, which are the losses arising from the hydraulics within the waterway.
Yeah. Again, I'll ask you to explain, right? So hydropower basically takes the energy that's stored in a reservoir or a kinetic energy on a river flow, right? So you take that, turn into some mechanical way and turn into electricity. So sometime you might have coming from a far away. So that's why you need a tunnel to bring it and have a very high impact. And then you have a huge reservoir and then the turbine moving very slowly, sometimes very fast, depending on the water head. Do you want to explain in simple terms so for some of the listeners?
So essentially we start off with the kinetic energy that results from lifting a mass a certain distance above the earth.
The potential energy.
The potential energy. And then we recover that energy by that water flowing back down through a waterway, and we convert it into mechanical energy by either of two paths. One is what we call the impulse machine. So that's where we accelerate that water to a very high velocity using the very high pressure that's available due to a very large change in elevation. And that hits a bucket, and the impulse of that and the change in direction of that results in that wheel turning around. And the efficiency is not as high using that method, but it does allow us to exploit a very large elevation difference, so in a very high pressure. And that's mainly in machines that are in the family of machines we call Pelton turbines. So they have a row of buckets on a wheel. The other more widely applied machine is a reaction machine where we push water through a water passage and force it to change direction. And at the same time, we initially accelerate it to generate lift in the same way as we get lift on a wing of an aeroplane, except the wing is curved and fitted into a wheel, but the same principle. We get lift on one side, we get pressure on the other side, and that forces it to rotate. And then we try and recover as much energy in the stream of water coming out of that machine. So most of the energy goes into the wheel and not in the water that comes out. So those are the two primary methods. We do have also some machines that are more like a propeller, but they essentially are still acting as reaction machines. That wing, or that propeller blade flies through the water and generates suction on one side and pressure on the other, and that drives it round. So same sort of thing. Yeah. But in each case, we're converting the potential energy in the pressure in the water into kinetic energy, forcing a change in direction, and then extracting that as mechanical energy. And then that drives a shaft, which spins a generator and produces the electricity.
Yeah, because hydropower is all about using gravity. So gravity is the magic word. And I heard about that in the context of an electric vehicle. And the first time I experienced was quite amazing. So I was driving through rural New South Wales. So we are up in a hilltop. So you have a lot of potential energy there. Say my battery was 25% charged. I come down, hey, it's 30% charged by driving 30 odd kilometers, right? So you realize with the regen breaking, this potential energy got converted and got stored in the battery.
Yeah, and there have been numerous proposals by people to build gravity energy storage systems using solid masses like trains and blocks of concrete and all the rest of it. And the principle is the same, and there's nothing wrong with it in terms of whether it works or not, but it's just never going to be as efficient. Water flowing through a pipe is just such an elegant way to extract energy because you can control the losses to a very low level. Typically in a pumped hydro scheme, we'll have losses in the waterway of maybe 2 to 4%. We can control that down to a very low level, whereas if you're trying to control it with wheels on a rail or cables running on a pulley, all of those things, the mechanical efficiency is much lower. And water is so cheap that you can store vast amounts of energy in a fairly small volume. So again, it's why pumped hydro has been so successful in terms of energy storage.
Yeah, but now if you look at the other side of it, again, I was responsible for a large project in China, Fujian Hydro. It's a couple of thousand megawatt. I forgot exact number. And there's a 40,000 people got displaced at a huge area. Now, those things were very easy to do, maybe even 20 years ago. Of course, 50 or 100 years ago, it was much easier because the eminent rights, that the eminent domain, or what is called, that the government has a right, those rights are much stronger than people's right. Now it is very difficult to do a 2000 megawatt hydro anywhere in the world right now because you flood so many people. So what is the large hydro market right now? Are there many being built?
Yeah, look, attention is turned back to pumped hydro for exactly that reason. Solar is so cheap now to generate the primary energy using solar and then to store it using pumped hydro just makes so much sense. If you can imagine running 1,000 or 2,000 megawatts for the whole year, the amount of water that flows through that is immense. And so the size of the storage has to be immense. Whereas if you think about you're recycling the water every day, straight away you can understand how much less water you need. And so that is one of the things that's driving pumped hydro, is the fact that it's so difficult to permit conventional hydro, whereas pumped hydro uses relatively such a tiny amount of water. For example, in Australia, the amount of water that you would need to fill every single pumped hydro that Australia has projected it might need, say 20,000 megawatts of pumped hydro in Australia, that would only require 1/10 of the amount of water that all the thermal stations use in a year. Relatively, it's a tiny amount of water. Ho, which is near me here, is 500 megawatts and 14 hours storage. And yet the storage reservoir at Splityard Creek is about 1/100th of the total storage of the Ivanhoe Dam, which is mainly for flood mitigation and water supply. So on a relative scale, the amount of water that we need is tiny. And then the other thing that's increasingly of interest, and I recently gave presentations at a conference in the US and also in Canada, is repurposing mine pits. And one of the projects which is under construction in Queensland is a project called Catchment, and that's 250 megawatts with 8 hours storage. And that's using a pair of gold mine pits where those pits are being mined out. And so there's a lot of interest in that because it means that you're using an area that's already disturbed. Therefore, you don't have to put a barrier on a river. But that's the other thing about pumped hydro as well, is that you can go offstream. You don't have to be on a river. In fact, very often you'll find better sites off rivers rather than on rivers, because if you can imagine, rivers follow the easiest path, and the easiest path may not be the most direct path. And yet for pumped hydro, we want to get to the most direct path between the upper reservoir and the lower reservoir. So it's not surprising at all that these off-stream pumped hydro schemes, very often much better schemes than if you dammed the river and tried to build on the river. And so consequently, it's very much easier to permit those smaller schemes. The other thing that's happening as well, particularly true in the US, people are starting to look at some of the very old conventional hydro schemes, many of which were quite small, 20, 30, 40 megawatts, but they involve quite large reservoir. And so people are starting to have a look at those same sites and saying, if we put in a pumped hydro, it could be 10, 20 times bigger using the same inundation area because you're using the water. Look, there's renewed interest, both because we need storage, but also because we're thinking that it's no longer acceptable, as you point out, to flood an area and displace very large numbers of people and disrupt the morphology of a river and the biology of the river as well. So it's focused attention in a different direction. I don't know whether you can see the background behind me there, that beautiful piece of river there. And that was going to be dammed for irrigation. Fortunately, that project didn't go ahead, but we are going ahead with a pumped hydro, which is more or less off-stream. It's downstream of an existing dam, which has already disrupted the flow. And so we're making use of a piece of the river that's already been impacted by irrigation and avoiding having to flood a beautiful area like that behind me.
And then most of these pumps will be using floating solar. Is that a fair assumption during daytime to pump back?
It probably won't be floating solar because in Australia, we have a lot of land area and we also have a growing interest in co-location of terrestrial solar with grazing animals on the same area that the solar is built. And that's very cost effective and the farmers like it because they get better returns from their grazing land because less evaporation, shelter for their animals. And so solar from those installations is very cheap. We've also got a surplus now in Australia very often of rooftop solar. Yep. Because something like a third of houses in Australia now have solar. If you're like me, you try and use it to charge your EVs, but you always have some left over. And so that's got to go somewhere. So increasingly, we're looking to use that for pumped hydro.
Okay, that's good. So you are saying for Australia, at least, all the pump hydros are either getting rooftop solar or you have agrovoltaic. Fantastic.
Yep. And of course, they can also use wind. So Snowy Hydro has got a long-term contract to buy wind as well as solar, and it uses that to offset its conventional hydro, but also to support its pumped hydro. So, yeah, you'll see more of those sort of deals happening as well, I think.
But for other countries, Australia is actually quite an exception with almost 6 kilowatt per capita solar. So it's a solar coming everywhere. But rest of the world, especially in emerging countries, is it fair to say when you are doing rehabilitation of, say, 50-year-old, 60-year-old hydropower, maybe it's worthwhile to see, let's put one of those pumps that can do both ways and maybe run them with a floating solar downstream or up?
Definitely. And Indonesia is considering that right at the moment. It's looking at floating solar combined with pumped hydro. It's also looking at nuclear and again, the pairing of nuclear and pumped hydro works very well. It's got to be all of the above type solution. And certainly, as you say, many countries are not as fortunate as we are. When you look at, say, Canada is going to use a combination of conventional hydro and pumped hydro. The pumped hydro will really be insurance against the seasons when the snowfall is meager or it melts early because of climate change. So we're seeing different countries will use different things. The number of countries that actually have nuclear is relatively small. It's something like 30 countries out of all the countries in the world. And for most countries, nuclear is a fringe player. But if you combine it with pumped hydro, you can make it really quite effective. So I think it will vary across the world. In the UK, they're looking at vastly expanding their wind, and wind generally will require less storage. But when you have a wind drought, then you will need storage. They're going to be looking at quite a different solution to their storage problem than perhaps other parts of the world. And in some of those places, interconnections are probably going to be more important than local storage. So you see, for example, Norway has got a lot of conventional hydro, is looking at pumped hydro, and that can be used to offset wind and solar from other parts of the continent.
Yes, pumped hydro getting mainstream, and in where you have solar. So that combinations work very well. Ultimately, gravity is the ultimate storage, right?
Yep, pretty well. Everything else is ultimately not sustainable. That's the bottom line. And even chemical storage in batteries, ultimately, the laws of thermodynamics tell you that eventually it'll run down, and that means you've got to recycle and rebuild, and that means energy input. That's why I think it's got to be horses for courses. If you need large amounts of bulk storage, then gravity is the best way to do it. If you need mobile storage, of course, then gravity is help you out. And that's where chemical storage comes in.
No, but there was one UK startup, I think about maybe 10 years ago, called Gravity-Power. So I saw those videos that you take a big 10 or 20 kilowatt weight and lift it up, and it slowly comes down and the pulley runs the light for 2-3 hours. Promoting to electrify rural Africa. I don't know where it is, but it was quite interesting.
Unfortunately, you don't get a lot of energy. People often don't quite understand how much mass you need to lift and how much you have to lift it to store even quite a small amount of energy. As a demonstration and a training exercise, we have in Brisbane and in Melbourne through an organisation called Construction Area, we have built 2 small-scale water batteries, and they generate about 50 watts for about 4 hours. But to do that, we need 20,000 litres of water in each of the tanks. Or we need 2 20,000 litre tanks. We fill one of them up with water, and we pump the water up there by solar during the day, and then during the evening we run down through a little micro turbine and generate power and run some LED lights. But it illustrates to the young professionals very graphically how much you have to store. The head we have in the tower, the steel tower that supports the tank, is only 10 meters. So they do the calculations and realize that 10 meters times 20,000 liters of water times the efficiency of a very small machine like that doesn't give you many hours of LED lights.
Now, you have really touched into something I always wanted to do. I had a crazy idea when I was in high school saying, because the water tank is very common all over Asia, that storage, are saying, if you use somehow electricity up and this water will run down. So I'm just thinking, if you take your water battery to the next level, right now I'm on a 30th floor. So if the whole apartment, say a 300 square meter apartment with a 10 meter height, so it's about 3,000 cubic meter, right? And if that was filled with a rooftop solar and gradually trickled down to ground floor as a water battery, will produce something, right?
Yeah. I usually say to people, a very rough rule of thumb, which works for large hydro because of the fact that the efficiency is that if you take the number of megawatt hours stored, multiply by 0.4 and divide by the head, you end with the volume of water in gigaliters. Now, that becomes increasingly inaccurate. In other words, the amount of water you need increases as you get smaller and smaller scale, and you get more losses in the pipe work, and you get lower efficiency. Like our little turbine in the water battery demonstration, I think has got a best efficiency of about 60%. And we probably have at least 10% losses in the pipework. It struggles, but it's very easy to calculate approximately how much water you need. But the bottom line is that 20,000 litres or 20 cubic metres doesn't last very long in a small system. So that's the drawback. And that's why, by and large, you're better off putting the pump storage somewhere where you've got convenient topography, where you can get the land and you can build it at a slightly bigger scale and get the efficiency.
No, but Mike, I will do some calculation and I'll post into LinkedIn just for the fun of it, water battery, and I'll tag you so that we can have a bit of conversation.
And if you look in my posts, I'm sure you'll find somewhere about the water battery and construction area. It's a really tremendous program, and the young professionals really enjoy it because they have to role play being a contractor and bidding for the job, and then they have to assemble the whole water battery from pieces and then commission it, and they have to all the time be mindful of safety and organisation, and then they finish off with a barbecue. And I love going out and meeting the young professionals that have gone through it and talking to them about energy and storage. Is very fulfilling.
Yep, thank you. Because I interviewed Emily Morris. She's the CEO of a small micro hydro company out of Atlanta, Emergy. And she always keeps on saying hydropower is nature's battery, right? If it's a runoff river, because it give you 24/7, you don't have to store because it's always there. So what's your view on micro hydro? Why it's not taking up? Because large hydro, especially I worked in Central Asia, some part of China, this thing freezes. During winter time, you cannot run. Kyrgyz and Tajikistan, all those hydros freezes. Russia, large hydro, Canada, all of those will freeze. But the micro hydro, somehow the small stream keeps on running in many parts. What about micro hydro? Why is not taking it up? Because irrigation canals here and there.
I always say to people that if there's an opportunity for micro hydro and small hydro, it works if it's going to benefit an owner who can build it themselves and who has the alternative of quite expensive power otherwise. When you look at the price that, say, Canada sells hydropower to the US, it's so low that you couldn't do that yourself as an individual because the capital costs would just be too high. And so I suppose the key issue is if you've got a suitable site and you could build it yourself, and we promoted this in Papua New Guinea when I lived there, these small schemes to benefit a local village when we knew that the alternative of taking power in there and running it was going to be too high. But it's the sad story with a lot of micro hydro, and this is true. I saw this in Nepal, in Papua New Guinea, in Indonesia, is that the failure rate of these schemes is very high because very often they don't have the benefit of good engineering, and they're also very vulnerable to floods. And you only need a very large flood to come through and wash out a weir. And very often the owners don't have the energy or the capital to rebuild. So that's the problem in micro hydro. It's a lovely idea. And if you can build it yourself, some of these micro hydro schemes that have been built and looked after carefully have run for very long periods. One of our clients owns one in southern New South Wales, and that was built in the 50s, and it's still running now. Beautiful old power stations, except for the asbestos paneling in the walls and the roof. But yeah, beautiful little schemes and really quite unobtrusive, very low impact on the environment by and large. But that's, I guess, not a common situation to find just the right site.
You're saying it's a technical challenge, because I remember we installed one in Sumatra, tiny 250 kilowatt system running on a small canal, and there's a PPA with PLN, the power utility, and they were making $5,000 a month by selling. My numbers may be a bit rubbery, but it was a lovely little community asset for the local communities, and money was coming from nowhere because these irrigation canals were going at a very high speed from that point anyway, taken off from a river.
Yeah, look, if you can do it And there's a couple of them in Australia that now, these days, are doing very well because our pool prices at the peak will go to $17,500 per megawatt hour. And we've got clients that have made millions in a weekend where the power price went high and they were fortunate. But that's become harder to engineer, and the numbers are always at risk, whereas the large-scale pumped hydros can secure their future a bit more solidly with a PPA to a diversified utility. And that's an interesting point, actually, is that an organisation like Snowy Hydro and increasingly some other owners of pumped hydro, the value in it is actually as insurance against those very high price periods. And so they value it not by how much energy it generates, but by how much they save in terms of insurance. And it allows them to run other plant right to the limit, knowing that if that other plant falls over, they can start the hydro very quickly. It's not unusual to have hydros that can be synchronized in under 2 minutes. And it means that if you lose generation within a 5-minute trading interval, you can be back online. Its value has changed in that way. And nuclear is a bit the same. If you can keep your nuclear running at 98% output all the time, you can make money. But to do that, you need to have a reserve in case for that 2% of the time it falls over.
Yeah, I mean, those value of lost load sort of prices, those are just to provide market signal. No one should invest in a market based on those prices. And I'm of the view that the way home batteries are coming in, the way the vehicle to grids are coming in, those imperfections, lack of a better word, will very quickly vanish. Very quickly.
Yeah, I don't know. See, one of the problems is that most of the interruptions to power occur within the distribution system. And so if too much of your storage is actually embedded in the distribution system, you actually effectively don't reduce the risk very much at all. And certainly for large commercial and industrial loads, they can't afford to be relying on a storage element within that's embedded in the distribution system, simply because the fact that something like 90% of the interruptions are occurring within the distribution system. Although it'll be fantastic when we do have V2G, especially if it's widespread. And we certainly, at the moment, I've just been looking at our home battery systems for myself and for my daughter. So personally, for the 30% odd of the energy that's consumed by households, it will be an enormous benefit. But for large industrial and commercial users, I think the benefit will be quite significantly attenuated simply because the distribution system is unreliable or relatively unreliable. And I expect that may get worse because when you have very large numbers of EVs charging off the network, if they start to trip in the same way as we found with inverters in the early days, if a high voltage spike occurs and all those loads start to trip, then the whole system could collapse quite quickly. So I think if you're running a data center, you want something more robust than that. And it's interesting that Google has just signed a contract for 3,000 megawatts of hydro in the US, and a significant amount of that is pumped hydro. And the reason being that it realizes that if it can have a direct connection to those hydros on the transmission system is very much more reliable than the distribution system. So I think, again, it's having that mix of possibilities and technologies that gives us the robustness that we need, that gives us the reliability. But it's very much a crystal ball.
But at the same time, the sort of load curve at a terminal station level, dominated by residential customers, will gradually become very flat with the home batteries and everything else. So that will also change the system shape. Still, residential is 30% of the load. One cannot ignore that. And residential is where all the rooftop solars are, right? Yeah, it is very complicated, but a lot of interesting thing will come out of this transition. And Australia is leading. That's amazing. Is there anything else you want to highlight?
The one other thing that I would say about pumped hydro, and this is one thing that we are at pains to emphasize, is that one of the great things about pumped hydro with its relatively small reservoirs is that the smallness of those reservoirs means that the quality of catchment management has to be very high. We can't afford to have bushfires leading to runoff, leading to sedimentation of those reservoirs. And we fully anticipate that will mean that these pumped hydros, in order to get their social license, will also be required and will have the revenue and will have the business case to support much better catchment management than we've had in the past. And some of our catchments that have been heavily logged in the past and where fire management has been very poor and where we've seen rivers choked up with runoff after fires, that won't be able to continue because the pumped hydros will have to, for their own business, do better, but they will also have the revenue to do better. And what I'm hoping is that will then lead to much more involvement of First Nations people, Indigenous people who have got a long tradition of fire management and understand the benefits of cold burns. And I'm hoping that they will get involved and that we'll see employment by them to do a lot of that catchment management. And I'm hoping that catchment management then will result in re-establishment of populations of indigenous flora and fauna, as we've seen in some parts of the world where areas have been properly managed and apex predators brought back in. And lo and behold, we see a whole regeneration of areas. So that's one of the environmental aspects of pumped hydro that I'm looking forward to seeing as well. And we're seeing that already. We've got a site that has been horribly damaged by sheep and then by goat farming. And in the future, that land will be quarantined from grazing. And as a result, there will be an opportunity to re-establish the native habitats and fauna and flora, including some endangered species. So, yeah, that's one sort of hidden benefit of looking at pumped hydro.
Okay, now that you prompted, if you have a few more minutes, I have a couple of just one that intrigued me, slightly related, the impact on climate change. Toktogul in Kyrgyz Republic, this is about 1,300 megawatt, and it's a huge catchment area, 50 years old. Now, the numbers that I have seen, and I have seen the water level when I was a project officer going every year, gradually not enough rain, not enough surface runoff to hold it there. So one of the ideas I was toying with, and I hope the government does it now, is to do a massive tree planting. At least you retain some moisture. Are you involved in any of the projects where you send drones to plant trees upstream? I know in Canberra, I've seen one company is doing it, but are you doing as a part of a project, Hydropower?
Not within the projects I've been working on. As I say, most of the projects we're working on at the moment are pumped hydro, and we're hoping that this idea of fire management and catchment management will become part of those as they go forward. But certainly it's of considerable concern in Quebec, for example, and also BC Hydro in British Columbia has also done studies of the impact of climate change on the yield of their catchment, because they have two problems with climate change. One is that the snowfalls are much more erratic, and so they can't rely on them to the same extent. And the second problem is that if the weather is also erratic and they get spells of high temperature and it melts the snow prematurely, it means they lose a very significant part of their storage. And so hence they are looking at, in Quebec, they're looking at pumped hydro to offset some of that impact. And they're able to look, in Quebec, they're able to look at very large schemes. 1 or 2 gigawatts for 24 hours is not very difficult because of their topography. So I think in Canada, we'll see some of that sort of thing happening. But we're hoping also in the US that the enormous numbers of abandoned mine sites might also be looked at. And as a result, there will be revenue that will be able to be applied to minimising the pollution arising from those abandoned mines, and also some catchment regeneration. But it's all in the future at the moment. It's a bit we hope for, but haven't seen yet.
Good, thank you. One other item, experts like yourself, it's very hard to find these days. And is it being replenished very well? How are the younger generation coming in? Many people studying hydropower?
Look, it's becoming increasingly of interest, but it's one of those things, we lost a whole generation really. And my generation, more increasingly, we're retired, or some of us have died. And it has been a concern for me that we have this missing generation. But I'm very pleased to see, and of course, it's an important part of my job, is to encourage young engineers to take an interest in pumped hydro and to think seriously about the needs of storage, and to think also the needs for sustainability and environmental management, and the fact that the life cycle carbon embodiment within pumped hydro is a tiny fraction of that for batteries. And so consequently, if we're serious about reducing carbon emissions, then pumped hydro has to be part of the thinking.
Pump hydro and solar, yeah.
Yep, very much.
Thank you so much for your time. Thank you.
My pleasure. My pleasure.
We hope you enjoyed this episode of Energypreneurs. If you enjoyed this, don't forget the full video is on YouTube. Just search Energypreneurs. Thank you. See you next time.